Swayam Prabha. Digital India. Educated India.
This is your effective GM, and you can see that the effective GM of the transistor has reduced now by 1 plus GM-RS. So this is your effective GM. So this reduces by adding RS. Now we will do similar analysis like before. We will look at the impact of output resistance of the transistor, Rout. This particular analysis for MOSFET is extremely important. So please pay close attention. So what we are trying to figure out is, if I have a transistor like this, and if I add a source resistance Rs, then what happens to my Rout? This being my Vi. Again, draw the small signal. And in this case, we are looking at impact of Rout of the transistor, output resistance of the transistor, source resistance degeneration, and we are trying to figure out what is the output resistance, effective output resistance of the stage after adding Rs. So we will have a test voltage source connected at the output, and we are going to measure what is my test current. We will redraw this again to simplify. So what will happen again here is, just like the bipolar example, the sign of the current source will flip and the sign of the voltage source will flip, and that will make our life easier. Since I am noting voltage as Vs like this, source voltage here, the current source will flip its sign. It will look like Gm times Vs. When you look at this voltage right here, when you plot it here, it becomes this way. So we have just flipped it over here, the sign, and as a result of which we have flipped the current source arrow. You can start writing the equations, pause the video and start writing the equations, and at the end we will compare your final result with mine. Let's go through the equations and make sure you can follow what I have done so far. So the first equation is, what is the voltage across the resistor Rs? That is given by this IT current flowing through Rs, which is going to give you IT times Rs. Current through Rout is going to be this current and this current, which is GmVs. So this is that expression, GmVs plus IT. And then we can substitute for Vs from this expression, and that will give you Gm times ITRS plus IT. Vt is going to be the drop across this resistor plus drop across Rs. So that's given here. And then you can reformat this equation a little bit to get this particular equation. What you see in this underlined equation is you have 1 plus Gm Rout for the transistor. And we know that Gm Rout is a self gain of the transistor, and it's a large number, much greater than 1. So we can ignore the 1 to draw our insights. And here you can see this is our effective output resistance. Originally, without Rs, Rout was going to be equal to Ro. Now we have a gain multiplier effect over here, transistor self gain, Gm Rout. So the resistance which is added in the source gets multiplied by the self gain of the transistor. What is the self gain of the transistor? Is Gm Rout. So here we can see the Rout resistance looking down is the original Rout of the transistor, output resistance of the transistor, plus GM Rout times RS. So the key insight here is, again, by doing source degeneration, we are able to increase the output resistance of this stage of the transistor. So we use this trick quite a lot when we want to have higher output resistance, to boost the output resistance. So let's recap again what we did, because these insights are the ones which we have to carry forward. Every time you don't have to do all the equations. The first time you see a new circuit, you do the equations and you draw the insights, but you use those insights over and over again for your paper design. If you just have a bipolar transistor and you do emitter degeneration, RE, what happened then? Our Rin was originally R pi beta times Re. So whatever is in the emitter gets multiplied by the beta of the transistor in case of bipolar, when you are looking at the input resistance Rin. So adding resistance Re at the emitter, we are able to increase the input resistance of the stage. Similarly, we also learned that output resistance Rout, which is looking out this way, also increases. With some approximation, Rout is going to be equal to Rout plus GM Rout times Re. So whatever is in the emitter Re resistance, that gets multiplied by the GM Rout, which is self gain of this bipolar transistor, and the Rout goes up. So both these parameters, Rin and Rout, they increase by adding emitter degeneration, and the gain became minus GM divided by 1 plus GM Re times RL. So what we said is, this is our effective GM, which degraded because of the emitter degeneration. We did same analysis for common source amplifier. With source degeneration. In this case, we don't really care about Rin because it's infinite. The gain became minus GM divided by 1 plus GM RS times RL. Again, in this case, we have source degeneration will degrade your GM, will reduce your GM by this factor, and your output resistance, looking down, Rout, used to be simply the transistor Rout, and now it got a bump, GM Rout times RS. Again, these are some approximations we have done here just to keep consistent insights. So whatever is in the emitter, whatever is in the source or emitter, gets multiplied by the self gain of the transistor when you look at the output resistance. And this is an important factor, because there are many circuits when we are trying to increase the output resistance, which you will see in future. We badly need high output resistance. For example, if you are making a current source, then you want as high output resistance as possible. So you use this trick to improve your current source. So these are the summary insights from what we did so far. Next, we are going to take it a little further. I'm going to teach you how to just look at a configuration and figure out some key characteristics of that configuration. Let's start with a simple example. We'll start with a bipolar transistor, and what we are trying to do is, here we're trying to figure out what is the Rin in this circuit. You can do small signal analysis and figure out the Rin expression, but by just looking at it, you should be able to tell that this Rin is going to be equal to, first is you have R pi in parallel with 1 over GM, because it's connected the way it is, in parallel with output resistance of the bipolar transistor. And out of all these three numbers, which one is the smallest? It's going to be dominatingly 1 over GM, because R pi is beta over GM, so it's 100 times larger. And R out, we already know for bipolar transistor, is quite large. Just by looking at this circuit, you should be able to tell that this Rin is going to be equal to 1 over GM. This is our quick first order approximation. This particular configuration is called a diode configuration. You may wonder why, and if you look carefully, you can see that this actually looks like a simple PN junction diode because the collector base junction is shorted out. Hence, it's called a diode configuration. Now, you can look at a similar configuration in case of a MOSFET, and there what you would see is this circuit that looks like this. I would like you to go through small signal model of this circuit and figure out what is the R out looking in, or you could say Rn actually, input resistance here. What is the resistance looking in into this transistor? So draw the small signal model for this and tell me, you can pause the video and tell what is the Rin going to look like. So as I have shown you, I'm sure you got the same answer, hopefully. The Rin is given by parallel combination of 1 over GM with R out. Another trick I can show you is whenever you're doing circuit analysis and you see elements coming in parallel, then you suddenly switch your mode of operation to conductance rather than resistance. So in this case, you could say that my G in is equal to GM plus G out. G out being reciprocal of R out. And this becomes very convenient to do the analysis. And at the final end, you can take reciprocal of G in if you need a resistance value. So since R out is very large, you can tell that R in will be equal to 1 over GM of the transistor. So these are all basic patterns that we are going to go through. As I have told you earlier, circuit design becomes like a pattern recognition so that you can design your circuits very quickly by putting these jigsaw piece puzzles of patterns. And by doing this exercise again and again, you become expert at it. So even if I give you a 1000 transistor complicated circuit, within 10 minutes you should be able to tell what's going on from input to output. Next concept that we had learned was if you take a transistor, for example, if we take a MOSFET transistor and if we add a resistance at the source Rs, then the output resistance R out here looking in, that becomes R out plus GM R out times Rs. That's the key concept. Now let's see what happens when you use different implementation of Rs. In a integrated circuit environment, we may not want to use a resistance because the resistance Rs and the transistor, they are two different steps in the fabrication process. So you would like to use something that matches very well, and sometimes you may want to use a transistor instead of Rs to implement the resistance. So we could start with an example. First example would be, let's say we did this. What would be R out here if this is my V input? We just learned some time ago that this is 1 divided by GM. Let's call it M2, M1. So this would be GM2 and parallel with RO2. And we say this is close to 1 over GM2 for our paper design. Then our R out is going to be equal to R out 1 of this transistor plus GM1 R out 1 of this transistor again times Rs, which in this case is going to be 1 divided by GM2. So this is representing our RS value. So in this case, you can see quickly, it will become RO1 plus GM1 divided by GM2 times RO1. Now if GM1 and GM2 are same, identical devices carrying identical current, then they will be same, right? So then this will be equal to 2 times RO1, if that's the case. The next example we're going to go through is going to be looking like this. And we're trying to figure out what is the R out here. Let's assume that both inputs of the transistor, they are AC ground. In this case, we can tell that the resistance looking down here is going to be R out of transistor M2, and that is going to get multiplied by the self gain of this transistor. So we can quickly recognize this pattern and say that my R out is going to be equal to RO1 plus GM1 RO1 multiplied by RO2. Again, GM1 RO1 is the self gain of this transistor. This is our source resistance RS. So here we can say that all GMs and ROs are comparable. Then of course GM R out is a large number, so we can ignore this RO1 and this will look like GM1 RO1 RO2. So this would be a multiplier effect. So we are multiplying the output resistance of transistor M2 by self gain of transistor M1. And as we have seen earlier, this number can be 10 to 50 depending upon what you design. So you can see that suddenly we have increased the output resistance looking down 10 to 50 times depending upon the self gain of the transistor, which is GM-R out. This particular configuration is called cascode configuration. Pay attention to the spelling. It's not cascade, it's cascode. So what cascoding is doing is it bumps up the output resistance by self gain of the transistor, which is GM-R out. As I said again, this is an important feature which is very useful when you want to increase the output resistance of a circuit. For example, for a current source, or if you want to increase gain substantially, then you would increase the output resistance and that would increase your gain. We're going to see all those examples as we go along. I'm going to extend this example one more time and I would like you to come up with the answer while I pause the video. First, let me draw the schematic. The schematic looks like this. Your job is to find out what is the resistance looking down in this configuration. How would you do that? If you try to do this using a small signal analysis, you'll take maybe an hour or so. But again, as I have told you before, we are trying to do pattern recognition, and using pattern recognition, we should be able to tell what is the R out of this circuit. So what is the first thing we note? The resistance looking down over here is going to be equal to RO3. Then in that case, what is the resistance looking down here? At the drain of M2, that will be self gain of the transistor M2, which is GM2 times RO2 times RO3. And the next step is going to be this R out will be equal to GM1 times RO1 multiplied by GM2 multiplied by RO2 times RO3. So now we can see that we have a bumper effect here. This is gain GM-R out. This is another gain GM-R out. So we are getting an output resistance which is multiplied by square of the gain, square of two transistors. So for example, if this GM-R out is, let's pick a number, 50, and if this GM-R out is also 50, then we have increased the output resistance by 2500 times, which is a lot. So we can use this trick whenever we want to bump up our output resistance. This particular configuration is called, interestingly, triple cascode. The reason I say interestingly is because if you just have a single cascode, we don't call it a double cascode. We just call it a cascode. So if you had only M2 transistor, then we call it a cascode transistor. In this case, M2 would be the cascode transistor. In the triple cascode, M1 and M2 are the cascode transistors. M1 and M2, they are called cascode transistors. I would like to wrap up this lecture by giving you an important exercise where you will have to do the analysis on a piece of paper by yourself, and this is an important self-learning for you. For what it's worth, I'm pretty sure I'm going to give you an exam problem based on this. Now that I have got your attention, this is what I would like you to do on your own. What I would like you to do is repeat this analysis for a bipolar transistor. First, we look at R out, and then we look at again R out, and then we do the same thing for cascoding like this.